All right, so this time what we're going to be looking at is dealing with limits again and properties of limits. Now, on page 40 of the textbook, which is posted on the website, you should be able to use the properties when needed. Nothing too crazy with the properties. For example, number one here, I have determine the limit as x approaches 5, where you have the square root of x squared divided by x minus 1. Now, using the properties of limits, there are several ways to solve this limit, to find this limit. The first way is that when I'm finding this limit, well, I don't have to really do anything other than I could do a direct substitution because the denominator will not be 0 when I substitute into my function. And so if I substituted in, say, 5 for x, so we'd have 5 squared underneath. We'd have a 5 minus 1 in our denominator. And so what we'd be looking at is the square root 25 divided by 4. And with properties of square roots, you can square root the top, which would be 5, and you can also square root our denominator, which would be 2. So that is one way to find this limit. A second way, so we didn't really use any properties in that first one, but in the second one we can, in that you can divide up your square root. And so I could look at it as two separate limits, where I have the limit as x approaches 5, and I'd have the square root of x squared, and that would be divided by the limit, again, as x approaches 5, to the square root of x minus 1. Now, the top limit, again, there is no denominator that's going to be equal to 0, so I could just substitute in. And so again, 5 squared would be 25, so I'd have a square root of 25. And in my bottom limit, again, as x approaches 5, I could substitute and I'd have the square root of 5 minus 1, which of course would be 4. And just as we did before in this first step, square root of 25 is 5. The square root of 4 is 2. Another third way the properties could be used for this particular limit is that I could take the square root of the limit as x approaches 5 with x squared divided by x minus 1. So I'll find the limit first, then take the square root of our terms. And so again, what I'd be looking at is the square root. In our numerator, we would again have 5 squared, which would be our 25. And in the bottom, again, we'd have our 5 minus 1, which would be 4. And again, using the properties of a square root, I can square root the numerator, which again would be 5. And I can square root the denominator, which again would be 2. In each of these cases, I figured out the limit using different limit properties, but we always come back to the same answer. All right, now, again, just solving, what we're going to be looking at is solving different types of limits. And it says determine the limit as x approaches 4 of the function x squared plus 2x minus 24 divided by x minus 4 and sketch the function set. Now, the first thing is with this function is that it's clearly not continuous because I cannot put a 4 in the denominator, and or when I do put a 4 in our denominator, our function is undefined. So our function is not continuous. But what we want to do is determine that limit, and if we can, if it exists, and then sketch the function. So again, I have the limit as x approaches 4. Now, the only thing I'm going to be able to possibly do here is factor out the quadratic that we have in the numerator of our function. And so again, I'm going to use my chart method, where I have my first term in the top left, x squared, to factor this function. I have my last term in the top right. All right, and so when I have an x squared over here, I know that I'm going to have an x and an x. And let's see here, negative 24, two numbers that give me negative 24. And yet when I cross multiply, I get my 2x. Well, I'm going to use 6 and negative 4. Because x times negative 4, we get negative 4x plus 6x. That gives me my positive 2x. And so now in my numerator, now that I factored it, I could have x plus 6 times x minus 4. And as I said, in this case, it's possible, and it actually did happen, our x minus 4s are going to divide each other out. And so now I have my limit as x approaches 4. And now that those x minus 4s have divided each other out, I have an x plus 6. And with no denominator to worry about, I can plug in 4 and get 10, because 4 plus 6 equals 10. Now, what does that look like on the graph? What do we have here? Because I do have a limit of 10. I don't have my graph as 10. So let's see here. I'm going to say that every space is 5, because I just don't have enough room here. And let's say my y values, I'll say by 2s. Let's go by 2s here. And so it says as x approaches 4, we have a value of 10. Now, in this case, our function is undefined at x equals 4. And so what we're going to have is a open circle. But then the rest of our equation here is it's a linear equation, x plus 6. And so I have a y-intercept of 6 and a slope of 1. And so our function, in fact, here is a linear equation with point discontinuity. All right, so as the limit approaches from the left-hand side, it does get to 10. And as we approach x equals 4 from the right-hand side, we get 10. And so again, our limit exists, but yet our function has point discontinuity. All right, now we're going to look at a function that's a lot different than something we've looked at. And that is, whoops, down below here, is I have determined the limit as x approaches 2. We have the absolute value of x minus 2 divided by x minus 2 and sketch the function. Now, the reason this is difficult is because we have our absolute value function. And the key here with the absolute value function to realize is that, in fact, the absolute value is a piecewise function. Let's get some smaller writing here. What happened to my smaller writing? There we go. It's a piecewise function. And again, to remember that the absolute value, what it does is no matter what value you get inside of this absolute value, it gets turned to a positive. Now, if I was to write this as a piecewise function, I would have f of x. And again, our key number is 2 here, x equals 2. All right, now it has 2 pieces. Now, at the top, I'm just going to have an x minus 2, and our denominator is not going to change. It's an x minus 2, and that's what our function is going to be for all values where x is greater than or equal to 2. And the reason for that is that if you put any x value in the numerator that's greater than or equal to 2, that part of the function is always positive. So the absolute value doesn't have to do anything. But when we have x is less than 2, we have a different situation. Now, again, the denominator is not going to change. It's going to be x minus 2. All right, but in the numerator, if we had an x value that was less than 2, say a 1, well, inside the absolute value would be negative, and we need to turn it to a positive. To do that, for all x values less than 2, essentially, I would be just multiplying the numerator of x minus 2 by negative 1. Because for every x value in the numerator that's less than 2, it's always going to be negative. So to turn it to positive, just like an absolute value function does, I would multiply it by negative 1 or a negative sign. Now, in terms of our function here, of what we're looking at, oops, let's see here, there we go. Finding the limits, or how our function looks, I guess is that for x is greater than 2 or equal to 2, up here, don't have a very good diagram for that, greater than or equal to, well, 2 can't happen. That's undefined, right? So I'm going to put a open circle there. We'll get to that. But so if it's greater than 2, first of all, these two are going to x minus 2 and x minus 2 will divide each other out, and all we're going to have is a value of, 1 at x equals 2. Let me erase that. All right, so the black part, it's going to be x equals 1, but again, at x equals 2, exactly on x equals 2, it's undefined. But after that, it's 1. All right, because again, those x minus 2's divide each other out to give you 1. And then when it's x less than 2, again, we have our x minus 2's divide each other out, but we're left with this negative sign, which means it would be negative 1. And there we go, x is less than 2. So there's where our function is not defined at x equals 2, but yet we do have two values, or we have values for anything other than 2. And so there's our function. And again, this absolute value function would be discontinuous. It would actually have jump discontinuity. All right. Now, next up in our example 4 is a completely different type of limit that we haven't done yet.